Our planet is capable of unleashing extreme chaos. Volcanoes, earthquakes, hurricanes, and floods can cause untold devastation. We may think we've seen the worst Mother Nature can throw at us, but scientists struggling to understand these disasters are discovering evidence that even more extreme events have struck in the past.
So this is about 13 times more powerful than the Pompeii eruption.
They're uncovering clues that the worst catastrophes in history could strike again. More than 200 years ago, a disaster tore through the Caribbean.
This is by far the deadliest hurricane to ever impact the entire Caribbean.
The Great Hurricane of 1780 was both huge and powerful. But can we trace its impact using today's tools? Because it appears that storms are becoming more powerful.
We believe that there should be more intense storms, perhaps not as many of them happening, but when they do, they'll be stronger.
The clues are here, buried and hidden, beneath the waves and beneath the ground.
There's this whole history in here about what's happened over time.
Now, scientists and historians come together to scour our volatile Earth to find out if in the future there will be more killer hurricanes. Right now on Nova.
Major funding for NOVA is provided by the following.
Hurricanes, some of the most powerful natural forces on Earth, called typhoons or cyclones in the Pacific. These storms can build up over warm waters and can reach hundreds of miles across. Storms like Harvey, Irma, Maria, and Typhoon Haiyan are synonymous with death and destruction.
Hurricanes kill, on average, 10,000 people a year.
They can cause death. They can actually destroy infrastructures, entire cities.
It's just complete devastation. It's unbelievable.
In 2017, a series of catastrophic hurricanes, Harvey, Irma, and Maria, impacted millions of people in the U.S. and the Caribbean. Entire islands and the city of Houston were devastated. Is this the worst that nature can throw at us? To find out, scientists are hunting for clues in the distant past.
The more we understand about them, the better we can predict them.
They're unearthing evidence of the deadliest hurricane in Atlantic history, the Great Hurricane of 1780.
It destroyed every house in Barbados. And it devastated this massive fort.
That storm was truly exceptional.
And looking even further back in time, scientists are discovering that 1,000 years ago, major Atlantic hurricanes may have struck more often.
And then you get this really big layer here that dates to about 1,000 years ago.
So, were monster hurricanes more frequent or more powerful in the past? And what does this bode for the future? Two record-breaking hurricanes struck the Caribbean in September 2017. The first, Irma, leaves a trail of destruction across the islands of Barbuda, St. Martin, and St. John. Its 185-mile-an-hour winds blow for a record 37 hours. Then, less than 2 weeks later, comes Maria. Its sustained winds blast the entire island of Puerto Rico, destroying the power grid, water supply, roads, and cell towers. For weeks, millions are stranded in the dark, without clean water, food, gas, or phones. The terrible toll of these storms puts them in the record books. But there is growing evidence that hurricanes just as powerful could once have been more common. Wayne Neely, a meteorologist and historian, has come to the National Archives on the island of Barbados, the most easterly of all the Caribbean islands. He's here to investigate the deadliest Atlantic hurricane since records began, the Great Hurricane of 1780. According to historical documents, this storm was so destructive, it killed an estimated 22,000 people across the Caribbean. And on October 10th, 1780, the first place it strikes is the island of Barbados, then under British rule. In the records from the time, Wayne finds evidence of the human cost.
Here in this death record, you have 4,500 names of persons who died in this great hurricane of 1780. Elizabeth Finley, Thomas Fisher, Nehemiah Fish, William Folks, Richard Foster, Elizabeth Fort. These are a few names of persons who died in that storm in Barbados.
And in the archives, Wayne also finds a harrowing eyewitness account that describes the fate that likely befell many of these people. It's a letter written by the Commander-in-Chief of the British forces in the Leeward Islands.
This is a letter written to the King by Major General Warren. I do not believe that 10 houses are saved in the whole island. Whole families were buried in ruins of their habitations. Many, in attempting to escape, were maimed and disabled. The ground covered with mangled bodies of their friends and relations.
Almost all buildings, whether stone or wood, were torn apart.
That must have been a really great storm to destroy all the buildings on the island. So you can imagine the horror and the misery that the residents of Barbados felt during the peak of the storm. It was horrifying and horrific.
You have no home to go to, you have no food. The fresh water supply is now destroyed.
In 1780, the people of Barbados are far from the only victims. In the following days, the storm kills thousands more on islands to the north and west.
The whole region was devastated. Islands such as Martinique, St. Lucia, St. Vincent, and Grenada all reported death tolls from the storms.
The wind is going to destroy your plantations. It's going to destroy everything. You lose all your supplies.
In 1780, it's estimated that 22,000 people are killed immediately. Most of the victims are slaves brought over from Africa to work on the sugar plantations. Then, thousands more die in the aftermath from starvation and disease.
It's always the lowest end of the economic chain that feels the effects of these things first. The slaves are going to die off first, and most of them did.
Certainly, the 1780 hurricane was the deadliest hurricane we know about in the Western Hemisphere.
The records also reveal, just as in 2017, this storm was one of 3 devastating hurricanes that struck in quick succession.
1780 was a terrible year for hurricanes. There were 3 incredibly destructive ones.
Only a week earlier, another hurricane had struck the region. And then, just over a week later, another struck, also with catastrophic effect. But the death toll from the Great Hurricane overshadows them all. Even today, storms like Hurricane Katrina that struck the Gulf Coast in 2005, and Hurricane Mitch, the deadliest Atlantic hurricane in living memory, which hit Central America in 1998, can leave thousands dead in their wake. So what makes these killer storms so unusual? And will they become more frequent? Modern hurricanes like Harvey, Irma, and Maria are tracked by aircraft and weather satellites. What we've learned about them gives scientists an idea of how the 1780 storm likely formed and developed. On August 27th, 2017, 9 days before it makes landfall in the Caribbean, Irma begins as a storm off the west coast of Africa. As it travels west across the Atlantic Ocean, it quickly gathers strength. Heat rising from the warm ocean waters feeds energy into the storm system.
Hurricanes are like heat engines. They actually convert the energy from the ocean into motion in the hurricane.
Warm, moist air cools as it rises and then condenses.
That releases that energy that was carried away from the ocean, and that powers the storm.
And one of the reasons hurricanes are so intense is the ocean is very warm, and the air at the top of the hurricane is very cold.
These winds can then spin into a powerful cyclone, partly a product of Earth's rotation, with rain bands stretching hundreds of miles across. August 30th, as wind speeds reach 50 miles an hour, Irma becomes a named hurricane. Over the next 6 days, it intensifies rapidly. By the time it slams into tiny exposed Barbuda on September 6th, with sustained wind speeds of 185 miles an hour, Irma is a Category 5 hurricane. It's likely the Great Hurricane of 1780 formed in a similar way to this recent superstorm. But how strong did it get? Historians are able to piece together some details of the storm's strength, thanks in large part to ships' records, kept by competing naval powers. In 1780, the Caribbean is a battleground during the American Revolutionary War.
4 years earlier, the Americans had announced their independence, and the British decided, no, you don't. We're going to send a bunch of our troops over there to stop this.
In October, the area is full of British and European warships.
There was a lot of European ships in the area. You had the French, you had the Dutch and the Spanish fighting against the British warships for control of the Caribbean and the region.
Like the communities on the islands, these ships were vulnerable to violent hurricanes, as the British naval records in Barbados reveal.
Looking in the naval records, you can see the loss of so many ships. HMS Laurel, HMS Andromeda, HMS Steed Castle, all lost in the Great Hurricane of 1780.
The fate of HMS Deal Castle is depicted in paintings from the period. And historical documents reveal that thousands of sailors from all sides perished at sea. So given its devastating scale, was the Great Hurricane of 1780 more powerful than more recent killer storms?
We just don't know whether it was a uniquely powerful hurricane or whether it was just an ordinarily powerful hurricane that took a very destructive path.
Given the lack of scientific data, how can experts today track this megastorm from the past? Climate historian Mike Chenoweth has taken up the challenge. He's scouring old ship's logs, hunting for hidden clues. And he's uncovered an entry from October 9th, the day before the hurricane strikes Barbados.
One thing I found in doing the research was the first detection of the hurricane by the Spanish frigate Diana.
This is the earliest account we have of a ship encountering the Great Hurricane.
And so they were about 300 miles east of the island of Trinidad, off to the southeast of Barbados, at 10 degrees of latitude.
There bore down upon us a violent hurricane which lasted 48 hours without intermission. the wind ran the entire compass with violent gusts, and the frigate moved heavily in the swells.
So several days ahead of reaching Barbados had already become a hurricane.
But to quantify the strength of the hurricane, Mike faces a major problem. In 1780, there were no instruments for measuring the actual speed of the wind. The only clues are time of day, wind direction, and estimates of wind intensity. Mike continues with logs dated to October 10th.
This is at 6 in the morning. The hurricane has just finished devastating the island of Barbados. Everything is a complete wreck now. This ship plot here is for HMS Albemarle off the west coast of the island of Barbados. They have a hurricane blowing from the south on this map. That's the approximate center of the hurricane at this point in time. And then we have other ships off the coast of St. Lucia reporting northeast winds, and another ship approaching Martinique with an east-northeast wind.
Mike draws together records from all the ships and plots the position of the storm in 6-hour intervals. In this way, he tracks the storm as it moves across the Caribbean.
So from the 11th to the 15th, the storm is out in the eastern Caribbean, stirring up the water with this huge wind field that just continues to batter the islands all in the region.
For 9 days, the great hurricane ravages the Caribbean before passing into the North Atlantic. And Mike spots two features that made this storm so destructive. First, with hurricane-force winds that he estimates extended up to 75 miles out from the hurricane's eye, the storm was vast.
75 miles is about triple what we usually see for strong hurricanes in that area. The gale force winds extending out 220 miles to the north.
That means its strongest winds may have blasted an even greater area than Irma's. The storm was moving forwards unusually slowly, ravaging Barbados for 8 hours.
Because the storm was moving slower than average, it just had more opportunity to keep knocking more buildings down. You got thousands of people dead.
From the ship's logs, Mike is building up a more accurate picture of the path and size of the 1780 megastorm. But the logs can't answer the most pressing question. How powerful was this storm by comparison with hurricanes today? To answer this question, scientists are trying to understand how different conditions contribute to creating monster hurricanes.
You have a complex web of conditions that have to come together perfectly to produce this intensifying storm, and that's really a challenge.
Scientists agree there are 3 key ingredients for the perfect storm. First, for a hurricane to grow to great strength and power, there needs to be a layer of warm ocean water reaching down at least 200 feet.
Hurricanes churn up cold water from beneath the warm water on the surface. So they cool the surface. It's like throwing cold water on a fire.
Second, crosswinds near the top of the hurricane, called wind shear, can't be too strong, or they disrupt the formation of the storm.
That tends to blow dry air into the core of a hurricane. That also is like throwing cold water on the fire.
And third, hurricanes need moisture throughout the atmosphere. If all these conditions come together, wind speeds within the eye wall of the hurricane can rapidly rise.
They become the most powerful storms on the planet.
On a scale of 1 to 5, a major hurricane is a Category 3 storm or above, with wind speeds of 111 miles an hour or greater.
You could probably go outside and walk around in 75-mile-an-hour winds. I wouldn't recommend it. There's going to be things flying through the air. If it was a Cat 3 or 4 hurricane, you're not even going to be able to walk or stand.
Generally, if over half the buildings are knocked down, that's usually a good sign you got at least a Category 3 storm.
The deadliest storm ever to hit the United States was a Category 4 in Galveston, Texas in 1900, with estimates up to 12,000 dead. Category 5 storms are the most powerful hurricanes of all, with wind speeds over 156 miles an hour.
There are very few structures, boats, buildings, cars, that can withstand the force of a Category 5 hurricane.
As wind speeds increase, their destructive power grows even faster.
It's not a sort of linear change, it's actually exponential. So the wind is able to do a lot more work.
If you double the wind speed, you increase the destruction by at least a factor of 8.
So a Category 5 hurricane is at least 8 times more destructive than a Category 1. And recent history reveals the extreme destructiveness of these Category 5 storms. In 2017, Hurricane Maria wrecked power and water systems across most of Puerto Rico. Estimates put the damage at over $90 billion. In 1969, Camille blasted Mississippi, flattening hundreds of miles of coastline. And in 1935, one of the most intense hurricanes ever to hit the United States, the Great Labor Day Hurricane, ripped through the Florida Keys, killing over 400 people. But according to climatologist Mike Chenoweth, the Great Hurricane of 1780 devastated a wider area and left thousands more people dead than any of these modern Category 5 storms. And he's found detailed eyewitness accounts that reveal another reason why this unusually large and slow-moving storm was so destructive. Its power didn't come from the wind alone. Another devastating force in a tropical storm is the water. An intense surge from the sea, known as storm surge. This is what killed most people when Typhoon Haiyan slammed into the Philippines in 2013. In the Philippines, more than 60% of the population lives within a mile of the water. One of the most powerful storms ever to strike land, Haiyan's wind speeds reached 195 miles per hour as it moved slowly across the islands.
You have the wind driving this water towards the coast. As the storm is approaching landfall, it's going from deeper water to more shallow water. Many people lost their lives in that storm because of the surge.
Along any coastline, tsunami-like waves pushed on shore by hurricane winds can threaten lives and property.
And what you see is a wall of water that just wipes out the neighboring houses and trees and everything before it.
And in some cases, this storm surge can be 10 to 20 feet high, and anything within several feet to up to a mile or so of the coastline can essentially be wiped out.
Anybody that's told to evacuate because of the danger of a storm surge, they should not think twice about it. Just go.
Every year, millions of people in the U.S., Central America, and the Caribbean face the threat of hurricane storm surge. And it's storm surge that likely caused much of the destruction in Barbados in 1780.
Suddenly, these massive storm surges came to carry this incredible force with them and devastated the city.
Along the shore on Barbados, Wayne Neely is hunting for physical evidence of the storm surge in 1780. This is Fort Charles, just outside the capital, Bridgetown. It was entirely rebuilt after the 1780 hurricane completely destroyed the original.
In 1780, before the hurricane, the fort itself was a massive structure. The walls were much higher and were 3 to 4 feet thick. The size was immense. For the walls to be destroyed from that hurricane, it had to be a catastrophic storm.
The records describe an unusually high storm surge, over 25 feet. Eyewitness accounts tell us the hurricane swept heavy cannons 140 yards inland.
Nothing stood in place. It devastated this fort. It destroyed every house in Barbados, and it devastated the Caribbean.
We had entire fortresses and batteries of wharves, just totally swept away.
The scale of destruction reveals the extreme impact of the 1780 hurricane. And now, drawing together all the clues, it's possible to recreate what happened. On the night of October 9th, 1780, the Great Hurricane approaches Barbados from the southeast. The storm is over 300 miles across. On October 10th, winds and rains lash the island. Finally, as the eye wall approaches land, the huge winds push up a storm surge 25 feet high. It slams into the coast and inundates the land, ravaging the island for over 8 hours. It leaves more than 4,000 dead and goes on to claim a total of 22,000 lives across the Caribbean. The Great Hurricane of 1780 shows how devastating a hurricane can be in an exposed, low-lying landscape. Mike Chenoweth believes its destructiveness was unparalleled.
We haven't had a storm like that since. So we're talking about something that's happened only once in 400 years.
But what are the chances of it happening again?
We don't know how far back something similar might have happened, and we certainly don't know what that possibility in the future is.
Major hurricanes of Category 3 and above are not common events. On average, one makes landfall in the United States every 2 years. And Category 4 and 5 hurricanes are even less frequent.
Category 5 hurricanes are very rare. They're far, far more Category 1s than Category 5s.
But now, with the buildup of greenhouse gases in our atmosphere from burning fossil fuels, our climate is changing. So many scientists, like Carrie Emanuel, are predicting that intense hurricanes will become more frequent. But it's a challenging problem. Today, scientists rely on complex weather data from satellites and aircraft to create computer simulations that can help them make predictions. But this kind of precise data only goes back a few decades.
We have reasonably accurate data going back only to about 1970. And if you go back in time, we don't have satellites. And then if you go back before the 1940s, we don't have aircraft.
There just isn't enough modern data to discern patterns in hurricane behavior. Better data about hurricanes in the past would be valuable.
If we have understanding of the activity, the intensity, the frequency of storms 1,000, 2,000 years ago, then that gives us better confidence in our ability to assess what hurricanes are doing now and in the future.
But extracting clues about what hurricanes were doing thousands of years ago, well before detailed historic records, requires some very clever detective work. And some of it needs to be done at sea. Oceanographer Jeff Donnelly is looking for evidence of ancient hurricanes on the seafloor. His search has brought him over 1,200 miles west of Barbados to Jamaica. This is Discovery Bay on the northern coast. Jeff and his team want to expand our understanding of hurricanes by exploring the deep past.
We're looking into the sediments to sort of find these long-term records, to extend our knowledge back thousands of years.
Jeff focuses on one part of the bay, next to a reef, too shallow for the research vessel Atlantis. The only way to get there is by building a raft and towing it out to position. Their target? A blue hole. A natural sinkhole created in the limestone rock. Jeff is interested in the sediments trapped at the bottom of this hole.
The blue hole is really a good recorder of hurricanes, so it's sort of a nice time capsule. The sediment can go in, but it never can come back out.
On calm days, fine-grained silt and sand drift into the hole and accumulate over time. But the violent force of a major hurricane propels a different kind of debris into the hole.
When a hurricane will hit, you'll get really strong winds, big waves, storm surge. That all sort of comes up over the reef here, and there are really strong currents associated with that that will tear up pieces of coral and transport sand into a blue hole.
The more intense the hurricane, the larger the pieces of coral and sand the waves transport. And over thousands of years, this sediment builds up as layers inside the blue hole. The deeper the layers are, the further back in time they were laid down. The team lowers a hollow tube, vibrates it into the sediments, and retrieves the sample trapped inside. Back on board Atlantis, Donnelly cuts into the core.
So we basically can start at the top. You know, this might be what's depositing today, and then you go back further in time as you go down the core.
It's mostly fine, silty sand, but Jeff spots one sediment layer that's different.
When you get down to the bottom, this interval here, and there's really big bits of shell and coral fragments in there.
Washing and sieving the sample reveals larger pieces of coral mixed up in the sand.
It's quite coarse compared to the rest of the core. So this was all that material that was ripped up and washed into this basin.
To Jeff, the coarseness of the sediments is clear evidence of powerful waves, most likely driven by a major hurricane, striking here sometime in the past.
You'd have to have quite a high-energy event to be moving this kind of sediment from the barrier reef into that blue hole. 15-foot waves at something like an intense hurricane strike.
By retrieving organic materials washed in with the storm, like twigs and leaves that contain carbon, Jeff is able to radiocarbon date these coarser layers. It'll take months to know for sure when this hurricane struck. But he's dated layers from cores taken from sites all across the Caribbean.
So this is a piece of a sediment core that we took in the Bahamas. This particular section dates to the 18th century. See these light bands here, and here are these hurricane event beds. They're much coarser than the sediment around them. You can really feel the grit between your fingers.
And he's finding that the most recent layers exactly match up with the dates of modern hurricanes.
You start coming into it, with a healthy level of skepticism, but all the storms you expect to find end up being there.
That gives him confidence that his technique is valid. And now, he's finding evidence of hurricanes long before historic records began.
At present, we've been able to go back about 2,000 years at most sites. Every time we find a layer that dates to before 1600, 1700 AD, we're finding an event that we never knew occurred.
By plotting the dates of major hurricanes back 1,400 years into the past, Jeff sees a pattern emerge. For the first 700 years, during the height of Maya civilization, and as the Vikings were colonizing Greenland, it appears powerful hurricanes were more frequent than today.
They're not necessarily any more intense than the ones we've experienced today. They just occurred much more frequently.
Then, over the next 700 years, during the Renaissance in Europe, and as European settlers were arriving in the Americas, the record shows a marked decrease.
And then suddenly it shuts down.
The Great Hurricane of 1780 falls in the period where there appears to have been far fewer major hurricanes, making it even more unusual. So what caused this decline in hurricane activity beginning about 700 years ago? Jeff suspects it might be partly due to trends in sea surface temperature. And it turns out there's a way to recover ocean temperature data from the remains of tiny animals.
We can find out about sea surface temperatures in the past by looking at these fossil corals.
Corals build up giant colonies that can last for thousands of years. Cores drilled out from deep inside their structures reveal layers of growth.
These corals grow almost like trees, so each year it puts on a new band of growth, and you can actually count back in time.
While forming their skeletons, corals absorb oxygen from the seawater. Oxygen comes in two forms. Oxygen-16 has 8 protons and 8 neutrons in its nucleus, but oxygen-18 has 2 extra neutrons and is more abundant in the ocean when temperatures are colder. By measuring the ratio of these two forms of oxygen in the layers of a coral skeleton, scientists can calculate relative ocean temperatures over many thousands of years.
Using corals to reconstruct sea surface temperatures is really precise. We're able to reconstruct it right down to the year.
Plotting sea surface temperature for the Caribbean over the last 1,400 years also reveals a trend. The first 700 years look generally warmer than the next 700 years. The results match known historical and scientific records that chart a changing climate. From an era known today as the medieval warm period to a cooler period known as the Little Ice Age. And when Jeff compares sea surface temperatures to his graph of hurricane activity, it appears that in the past, whenever the sea's surface was warmer, there were more major hurricanes.
There are a whole variety of factors that can influence tropical cyclone activity or hurricane activity, but it's clear that there is this interaction between sea surface temperatures and hurricanes.
The pattern seems to fit what is known about hurricane formation.
The more energy available to power a storm, it makes sense that the storms are going to potentially get stronger.
But these findings present a puzzle. 1780, the year of the Great Hurricane, falls in the generally colder period of the Little Ice Age.
It appears at first blush to be quite an anomaly, the 1780 season. And actually, a couple of decades around it are actually one of the most active intervals.
But as Jeff looked more closely at the sea surface temperatures, he was able to detect a brief but noticeable spike in the decades around 1780. And cool temperatures in the atmosphere above, with warm ocean water below, is a known ingredient for hurricane formation.
Whenever you have two bodies of very different temperature, you can create a lot of energy that way.
So that might explain why in the middle of the Little Ice Age we see an increase in hurricane activity.
Jeff's work, linking hurricane events to ocean temperatures, could provide an explanation for the intensity of the 1780 hurricane. And this research could sound a warning for our future. Because modern data reveals that the sea surface temperature of the Atlantic is now higher than it was 1,000 years ago, and is still rising.
We're actually warmer than any point of the last millennium, just a fraction of a degree at this stage. But the projections are that that's going to continue. Not only is it warmer, but it's increasing faster at a faster rate than we've seen over the entire record.
As a result, will we see major hurricanes becoming more frequent?
We're likely to go back into one of those sort of intervals where we're getting lots more intense hurricane strikes.
The temperature of our oceans is warming. Greenhouse gases like carbon dioxide, generated by burning fossil fuels, are building up in our atmosphere. These insulate our planet, holding in more of the sun's heat, causing the oceans to warm more quickly than we've detected in the past.
The problem right now is that the rate at which we're pushing the climate system is very fast compared to anything that's happened in a very, very long time.
Whether this warming climate means there will be more Atlantic hurricanes is still an open question. But there is a growing agreement that the hurricanes that do hit will be stronger.
There's a pretty strong consensus that as the planet continues to warm, we're going to see a greater incidence of the high category hurricanes in most places.
We believe that there should be more intense storms, perhaps not as many of them happening, but when they do, they'll be stronger.
So can scientists predict where these strong hurricanes will strike? Amy Frappier, who studies ancient climates, has found an ingenious way to look into the past for answers. Compared to the last 4 centuries, she's finding that Atlantic hurricanes are on the move, likely heading towards the big coastal cities of the eastern United States. The evidence comes not from beneath the waves, but from caves under the ground. Locked inside stalagmites like these are the chemical traces of hurricanes from thousands of years ago.
So here's a stalagmite that we collected from Belize, where we know hurricanes have been part of the weather.
Rainwater that seeps through the ground above a cave dissolves minerals from the surrounding rock. Then, as it falls drop by drop from the ceiling, it leaves a little bit of this mineral behind, and a chemical signature of the rainwater itself. This forms stalagmites that over the years grow upwards from the cave floor. Back in her lab, Amy slices stalagmites open and polishes the surfaces. This reveals a series of distinct layers.
You can see that there's this whole history in here about what's happened over time. In this one, it's got lots of different changes in color and texture as we go from the older part to the younger part at the top.
Hunting for the chemical traces of a hurricane in these layers is possible. Because rain from hurricanes is chemically different from rain during ordinary storms. Again, a result thanks to the difference between oxygen-16 and oxygen-18, which has 2 extra neutrons in its nucleus. In an ordinary storm, raindrops evaporate slightly as they fall. The lighter oxygen-16 evaporates more readily, changing the proportions in rain hitting the ground. But in a hurricane, the air is so humid that there is very little evaporation. This means that in hurricane rain, there's more oxygen-16 than in weaker, short-lived rainstorms.
Whenever we see that light oxygen signature, we know that that is a fingerprint for a past hurricane.
To find this chemical signature, Amy isolates individual layers in the polished stalagmite, then drills out a minute sample as dust. A mass spectrometer can read out the chemical traces locked inside the dust. And it reveals which layers are richer in light oxygen, the signature of hurricane rain. The results are so accurate, They allow Amy to tell if a hurricane has hit in any given year, thousands of years in the past.
The level of detail is just unprecedented. We can see the difference between years with a storm strike in Belize and years without a storm strike in Belize.
With data from caves across the Caribbean, the evidence suggests that the paths of Atlantic hurricanes appear to be changing over time.
We're starting to be able to have enough data that we can see not only overall patterns of storm activity, but also changes in storm tracks.
Over a 450-year period, the average track of hurricanes has been moving ever closer to the continental United States.
400 years ago, the storm strikes were clustered in the Western Caribbean around Central America. And now the storm strikes seem to be happening much more frequently around the U.S. East Coast.
It's a trend that Amy is still exploring. But based on satellite data, Carrie Emanuel has come to a similar conclusion.
We discovered that over the last 35 years, the latitude at which tropical cyclones reach their peak intensity has been shifting away from the equator at a rate of about 35 miles per decade.
Carrie thinks that climate change is driving the recent shift.
What we see when we look at global warming is that the fastest warming is occurring in the Arctic. Hurricanes like warm waters, and so they're shifting toward the poles.
In just 30 years, that's over 100 miles closer to densely populated areas of the United States, along the eastern seaboard. The last major storm to hit the northeast coast was Megastorm Sandy in October 2012. After leaving a trail of destruction in the Caribbean, Sandy approaches the New York-New Jersey coastline. Though most of the Atlantic gets colder as you move north, Sandy feeds off a ribbon of warm water that keeps it alive, the Gulf Stream. This is a circulating current that pumps warm water from the Gulf of Mexico up and across the Atlantic. By the time Sandy strikes on October 29th, it's been downgraded from a Category 2 hurricane to a Category 1 storm. But as Sandy combines with another North Atlantic storm system, it hits with catastrophic impact. A 14-foot storm surge races into New York City, flooding streets, tunnels, and subways, and shorting out electrical transmission lines. Across New York and New Jersey, the storm leaves 60 people dead, damages 650,000 homes, and causes over $70 billion in damage.
It's just complete devastation, and you know, my parents have lived here for 40 years, and it's unbelievable.
Superstorm Sandy was massively large and hit a densely populated area. Its powerful storm surge did most of the damage, but its winds were not especially strong.
I think many people will be surprised to know that Hurricane Sandy, at the time it was impacting New York and New Jersey, was not considered a major hurricane.
Imagine if it had been a Category 3 or higher. It has happened before. The strongest recorded hurricane to strike this coast hit nearly 200 years ago. It is known in historical records as the 1821 Norfolk Long Island hurricane, and is now thought to have come ashore as a Category 4 storm, far more intense and extensive than Sandy. Experts estimate that if this storm struck today, it would cause over $100 billion in damage.
Imagine a Category 4 storm impacting New York. The flooding, the storm surge, the winds associated with that. Cities such as New York need to be prepared for this type of threat.
Many factors can affect hurricane formation. But as the climate warms, the threat of major hurricanes heading up from the Caribbean impacting the southern states and striking the northeast coast, is one that climate scientists are taking seriously. And they're highlighting a less well-known danger of global warming, one that will make hurricanes even more destructive. Warmer oceans cause water volume to expand. At the same time, glaciers are melting. The result, sea level around the world is rising.
And if you look at some of the more recent data, not only is it rising, in more recent decades, it's rising at a faster rate.
The best guess now is that if we don't curb emissions, we'll be up a meter or 3 feet by the end of the century.
The rising sea level increases the risk of damaging storm surge.
When that storm surge rides up on top of higher sea levels, then it causes a lot more destruction.
Today, millions of people in coastal and island communities are at risk.
With all of this infrastructure very close to sea level, we're much more vulnerable to much smaller changes.
To better understand our future, scientists are looking into the past. And what they're finding leads some to predict that a hurricane as deadly as the Great Storm of 1780, with its huge storm surges, will likely strike again.
We're going to see another hurricane like the Great Hurricane of 1780 again on our shores, and it's going to hit land at full intensity.
It's happened once before, so there's no reason to not expect it to happen again.
While there is no way to predict what lies ahead with certainty, the evidence suggests we need to be prepared to face more killer storms in the future. Floods in the past of unimaginable size and power
No one has ever witnessed anything even close in scale.
reshaped the Earth itself.
Floods that completely changed the face of the planet.
Today, scientists search for the evidence carved on the face of the planet and into the sea floor. Will they come again? Killer floods, next time on Nova.
This Nova program is available on DVD. To order, visit shoppbs.org or call 1-800-PLAY-PBS. Nova is also available for download on iTunes.